Jai Hind. Myself Nidhi Singh, Assistant Professor in Electrical and Electronics Engineering Department from Ajay Kumar Garg Engineering College. Today we will discuss single phase induction motor, which is topic from Unit 4th from Fundamentals of Electrical Engineering. This is first year subject. So starting with the contents. So in this lecture we will discuss the single phase induction motor and its construction. Then we will discuss double revolving field theory and types of single phase induction motor. So if we see this single phase induction motor, they are basically widely used in the ceiling fans, exhaust fan, refrigerator, washing machine, etc. And they require only single phase supply to the stator from a separate source. Then if we talk about the construction of single phase, so single phase induction motor is similar to that of three phase induction motor. The single phase motor stator has a laminated iron core with two windings which are arranged perpendicular. One is called the main winding and other is called auxiliary winding, or we also call it starting winding. And the motor uses a squirrel cage rotor which has a laminated iron core with slots in it, and single phase induction motor is not self starting and it requires some mechanism to assist it in the starting process. So if we see the stator of single phase induction motor has laminated stamping to reduce eddy current losses on its periphery, and the slotteds are provided on its stamping to carry stator, or we can say the main winding. The stampings are made up of silicon steel. This is to reduce the hysteresis loss, right? And when we apply a single phase AC supply to the stator winding, the magnetic field gets produced and the motor rotates at speed slightly less than the synchronous speed, which is denoted as ns. So now the other part is the rotor part. So the construction of rotor of this single phase induction motor, this is similar to the squirrel cage three phase induction motor. And the rotor is cylindrical and has slots all over its periphery, and the slots are not made parallel to each other. They are not made parallel to each other, but they are little bit squeezed. Here you can see, right, this is structure. So, and this squeezing, it prevents magnetic locking of stator and rotor teeth and makes the working of induction motor more smooth and quieter, means less noisy. And this squirrel cage rotor, it consists of aluminum or brass or copper bars. Here we have bars. Instead of winding, we use the bars. And these aluminum or copper bars, they are called rotor conductors and placed in slots on the periphery of the rotor. The copper or these aluminum rings, they are permanently short rings, short the rotor conductors called the end rings. We use the end rings. Here in previous slide, I can show you. Here you can see that these are the shorting ring, these are the end rings, and these are the conductor bar. This is the squirrel cage structure, and you can see it is squid in nature, right? Slightly shift. The cylindrical is slightly shifted. Then coming to the double revolving field theory. Now these single phase induction motors, they are not self starting, and this can be explained by using double revolving field theory. So according to this theory, any alternating quantity can be resolved in two rotating component which rotates in opposite direction, and each have magnitude as half of the maximum magnitude of the alternating quantity. And in case of single phase induction motor, the stator winding produces an alternating magnetic field having maximum magnitude, that is phi m. So here this so now according to double revolving field theory, now we can consider the two component of the stator flux, each having magnitude half of maximum magnitude of stator flux, that is phi m by 2, right. So here we can consider two components. Magnitude is half of the maximum one, means having the equal magnitude, and here both these components are rotating in opposite direction at the synchronous speed ns, which is dependent on frequency and stator pole. So here the two components, here we can see phi f and phi b. The magnitude is phi m by 2, half of the maximum flux. So phi f is the forward component, which is rotating anti-clockwise direction, and let phi b, here this phi b is the backward component and it is rotating in clockwise direction. So the resultant of these two component at any instant gives the instantaneous value of the stator flux at the instant. So resultant of these two is the original stator flux. So if we find the resultant of these two components, it will be the original stator flux. So here in this figure, if we find out the resultant, here we can see that both the components are in opposite direction. So resultant will be 0 and the angle is at 0 degree. So this is just the starting point. So here we will at this particular instant the value is 0. Now when theta is 90 degree, it means the 5, that is forward component, and backward component position will be like this. And if we find out the resultant, so resultant will be equal to, now both is in the same direction, so both will be added. So we will get phi m1 maximum flux, right? So means this value, we will get this value. So if there is a continuous rotation of the two component, it gives the original alternating flux. So we will get this original alternating flux, right? So now both the components are rotating and hence they will get cut by the rotor conductors. So now due to cutting of flux, EMF will get induced in rotor, so which circulates the rotor current, and the rotor current produces the rotor flux. Now this flux interacts with forward component phi f to produce a torque in one particular direction, say it is in anti-clockwise direction. Then the other component, that is phi b, which is a backward component, it will produces a torque in, suppose say, a clockwise direction, right? So if anti-clockwise torque is taken as positive, then we will take clockwise torque as negative. So at start, what will happen? These two torque will be equal in magnitude but opposite in direction, right? So both the torques will be equal in magnitude but they will be opposite in direction. So each torque, what will happen? Each torque will try to rotate the rotator in its own direction. Thus, the net torque experienced by the rotor is 0 at the start. So as both the torques which are getting produced here, they are opposite in direction and they are equal in magnitude also. So the torque will be 0 at the start, and hence the single phase induction motor are not self-starting. They are not self-starting. So here this is a torque speed characteristic. So it can be seen that at its start, here the n is equal to 0, and at that point resultant torque is 0. So here we can see that a single phase induction motor is not self-starting. This is torque due to backward field, this is torque due to forward field. So however, if the rotor is given an initial rotation in any direction, the resultant average torque increases in the direction in which rotor initially rotated, and motor starts rotating in that direction. But practically it is not possible to give initial torque to rotor externally, right? So there are some modifications are done in the construction of this single phase induction motor to make them self-starting. So we will see what are these different modification which we have done to make these single phase induction motor as self-starting. So there are different types of induction motor, and these types are basically on the starting methods, what method we are using to start these induction motor. So first is a split phase induction motor, then we have capacitor start induction motor, then we have capacitor start capacitor run induction motor, then we have shaded pole induction motor. So now coming to the split phase induction motor, here In addition to this main winding, here we can see that here we have a main winding. So in addition to this main winding, we have a auxiliary winding, or we called a starting winding. This is a auxiliary winding or a starting winding. So main winding is also called as a running winding. So we either called a main winding or running winding, and with this main winding and running winding, we have a auxiliary winding, or we can say a starting winding here. So this auxiliary winding, it carries a series resistance such that its impedance is highly resistive in nature, and the main winding is inductive in nature here. So let here the Im, this Im is the current which is through the main winding, and the Ist, here this current which is through the auxiliary winding. So if you want to draw the phasor, so first we will take V as a reference, as V is common in both the branches here, as both branches are in parallel. So taking V as a reference, here we know that the Im current which is flowing through the main winding, and the main winding is inductive in nature. So this current will lag with V by some angle phi m, right? So this will lag with some angle phi m. So here it is lagging with phi m angle Im. Now we want to draw this Ist. So now we know that this current is through the auxiliary winding, and this auxiliary winding is highly resistive. So it is highly resistive but not purely resistive. So it will lag this V by some small angle, right? So here if we draw the resultant of these two current, here we can see, here we can draw the resultant of these two current. So here we can see that these two current, right, these are separated with some angle phi. So thus there exists a phase difference of alpha between the two currents, and hence between the two fluxes produced by the two current. So the resultant of these two flux is a rotating magnetic field. So to produce a rotating magnetic field, the two components should be present, and due to this the starting torque, which acts only in one direction, is produced. So the motor will be started. So by adding this extra arrangement, we can start the motor. So the auxiliary winding has a centrifugal switch in series with it, and when motor gathers a speed of up to like 75 to 80% of the synchronous speed, centrifugal switch gets opened mechanically. So it gets opened mechanically, and in running condition, what will happen? This auxiliary winding remains out of the circuit. So we just add this circuit to start the motor. So motor run only on stator winding now. So auxiliary winding is designed for short time use, while the main winding is designed for the continuous use. So as the current, this Im and this Ist are splitted from each other by angle alpha at start, the motor is commonly called split phase motor. Here we are splitting the phases. Now coming to the application of split phase induction motor, the split phase induction motor have low starting current and moderate starting torque, and these motors are used in fans, blowers, centrifugal pumps, washing machines, grinder, latches, air conditioner, etc. So these are the applications of split phase induction motor. Now coming to the next, that is capacitor start induction motor and capacitor and induction motor. Now here the working principle, these are the two different methods, but the working principle of capacitor start induction motor is almost the same as capacitor start, capacitor run induction motor. Now in the previous case, that is in split phase induction motor, we have used the resistance for creating phase difference, right? And here what we are using? We are using capacitor for the same purpose. For creating a phase difference, here we are using capacitor instead of resistance. So we are familiar with the fact that current flowing through the capacitor leads the voltage. So if you want to draw the phasor of this So, taking V as a reference, and we know that this current, this IM, which is flowing through the main winding, so it will lag this V by some angle phi m. So, IM, because it is inductive in nature. And if we talk about this current, which is IST, which is flowing through the starting winding, this IST, this is flowing through the starting winding. So, as it is capacitive in nature, so current will lead this voltage. So, this current, this IST is leading this voltage. So, here this is the angle phi st, right. So, here again we can see, here the resultant is drawn, again here we can see that both the currents, they are separated with angle alpha. So, now there occur large phase angle difference between these two currents, we have seen in the phasor diagram, which produce a resultant current. This will produce a rotating magnetic field, since the torque produced by these motors depend upon the phase angle difference, which is almost 90 degree. So, these motors produce very high starting torque, and in case of capacitor start induction motor, the centrifugal switch is provided to disconnect the starting winding when the motor attains speed of 75 to 80% of the synchronous speed, right. But in case of capacitor start, capacitor run, right, capacitor start, capacitor induction motor, there is no centrifugal switch, there is no centrifugal switch. So, capacitor remains in the circuit and improves the power factor and running condition of single phase induction motor. So, this is the working principle of both the methods are seen. The only difference is that in capacitor start induction motor, capacitor start induction motor, there is a centrifugal switch and it will get disconnected when the motor achieves the speed of 75 to 80% of the synchronous speed. But in capacitor start, capacitor and induction motor, there is no centrifugal switch, the capacitor will remain in the circuit and it will improve the power factor. So, this capacitor will not get disconnected when the motor starts. So, this is the main difference. So, that is why it is called capacitor start, capacitor run. Capacitor run means it will remain in the circuit when the motor is running, but capacitor start induction motor means the capacitor is only used to start the induction motor, and all the working principle is same. Now, coming to the application of these method, these motor have high starting torque, hence they are used in conveyors, grinders, air conditioner, compressor for the heavy purposes. Now, coming to the shaded pole single phase induction motor. Here, the stator of the shaded pole single phase induction motor has salient, or we can say a projected pole. These poles are shaded by copper band or ring, which is inductive in nature. The poles are divided into two unequal halves. The smaller portion carries the copper band and is called the shaded portion of the pole. Here we can say, we can see in this diagram, this is the copper band. This portion is the copper band. This is the shading band, and the same structure is drawn here, right? The same structure, this pole is drawn here. We can see that. So, the main structure is here, right? So, these poles are divided in two unequal. These are the two unequal halves, and on one half we have a copper band, or we call it as a shading band. So, what is the purpose of this shading band, right? So, we know that the stator winding current is alternating in nature, and so is the flux produced by the stator current. So, to clearly understand the working of shaded pole induction motor, we will consider three reasons. Three reasons is, first, when flux changes its value from 0 to nearly maximum positive value, from here to here, right? From this to this is the first reason, right? Now, the second reason, when the flux remains almost constant at its maximum value. So, this reason, second reason. And the third, when the flux decreases from maximum positive value to 0. So, maximum positive value to 0 means from here to here. So, these are the 3 reasons which we have divided. Now, let us see what happened in these 3 reasons. So, in reason 1, when flux changes its value from 0 to nearly maximum positive value. So, in this reason, the rate of rising flux and current is very high. So, now according to Faraday's law, whenever there is a change in flux, EMF gets induced. Since the copper band is short circuited, the current starts flowing in the copper band due to this induced EMF, right? So, this current in the copper band produces its own flux. So, this will produce its own flux. Now, according to Lenz's law, the direction of this current in the copper band is such that it opposes its own cause. Own cause means it will oppose the rise in current. So, the shaded ring flux opposes the main flux, which leads to the crowding of flux in the non-shaded part of the stator, and the flux will weakens in the shaded part, right? So, this non-uniform distribution of flux causes the magnetic axis to shift in the middle of the non-shaded part here. Now, coming to the reason 2. So, when the flux remains almost constant at its maximum value, so in this reason, the rate of rising current and hence flux remains almost constant here, right? So, the rate of rising current is constant, so flux will remains almost constant here. So, hence there is very little induced EMF in the shaded portion. So, the very little induced EMF in the shaded portion, the flux produced by this induced EMF has no effect on main flux, and hence the distribution of flux remains uniform and the magnetic axis lies at the center of the pole. So, magnetic axis will lie at the center of the pole. So, in the previous case, the magnetic axis lies at the non-shaded area. Now, this is shifted from non-shaded to middle of this pole. Now, coming to the reason 3, here the flux is getting decreases from maximum positive value to 0, and in this reason the rate of decrease in the flux and hence current is very high. And now, according to Faraday's law, whenever there is a change in flux, EMF gets induced. Since the copper band is short circuited, now what will happen? The current starts flowing in the copper band due to this induced EMF. Now, again, this current in copper band produces its own flux. Now, according to Lenz's law, the direction of the current in copper band is such that it opposes its own cause, and now the cause is decrease in current. The cause is decrease in current. So, the shaded ring flux, what will happen? The shaded ring flux will aid the main flux, which leads to the crowding of flux in the shaded part of the stator. So, here you can see the crowding will be in the shaded part of the stator, right? So, this is the shaded part. This is the shaded part and the crowding of flux is in the shaded part. This non-uniform distribution of flux causes the magnetic axis to shift in middle of the poles of shaded part. So, magnetic axis will shift in middle of the shaded part here. This shifting of magnetic axis continues from negative cycle and leads to production of rotating magnetic field. So, this field's direction is from non-shaded part to the pole of the shaded part of the pole. So, we have seen in the first reason the magnetic axis was in this region, then it is shifted to middle of here and then it is shifted to this part, right? So, from here it is shifted to here, then here. So, this is nothing but rotating magnetic field. So, we have created a rotating magnetic field. So, the motor will start. Now, there are some disadvantages of this shaded pole induction motor. It has a low power factor. The low power factor is very low. Starting torque is very poor in this shaded pole. and the efficiency is very low as the copper losses are high due to presence of copper band, and the speed reversal is so difficult and expensive as it requires another set of copper rings. So now coming to the application of shaded pole motor here. Due to their low starting torque and reasonable cost, these motors are mostly employed in small instruments like hair dryer, toys, record player, small fan, electric clocks, etc. Right? And these motors are usually available in the range of 1/300 to 1/20 kilowatt. So these are the different methods of, we can say, different types of induction motor on the basis of methods which we are applying to start the induction motor. So in first method we have seen that we have used the auxiliary winding in addition to the main winding, and the auxiliary winding was resistive in nature. So we created two components to basically to produce the rotating magnetic field. Two components should be present. So we created two components to produce the rotating magnetic field. And in second method, that is capacitor start and capacitor run method, basically we have used the capacitor here to produce two components to establish the rotating magnetic field there. And the last method we have seen the shaded pole here, where we have used the copper band and we have produced the rotating magnetic field. So these are the different references which I have referred, that is I have referred D.P. Kothari and I.J. Nagraj of Basic Electrical Engineering. Then I have referred S.K. Bhattacharya of Basic Electrical and Electronics Engineering, and referred Uday A. Bakshi, Basic Electrical Engineering Technical Publication, and for the pictures I have taken from the Google from some technical sites. So that's all in today's lecture.